We've got a lot to do in this video to try and review conic sections. You might need to go back and check some other videos. You can find lots of other sources besides those on our assignment page. Okay, so picking up with question 31 on our semester review sheet, circle the type of conic section. Notice in this problem, if we FOILed and expanded, we would have a 1x squared and we'd have a 1y squared, and they are both positive. So that means that this will be a circle. So remember that this is a transformation of this circle. So the transformation then changes the center. So here in this circle with a radius of 7 and a center at 0, 0, think what happens in the one we're doing. The x now becomes x minus 2. So wouldn't we have to choose x to be positive 2 in order to get back to that same result of 0? And look at what we've changed in the y. It's y minus 3. So wouldn't we have to pick 3 for the y coordinate? The radius, of course, though, is still 7. So this number is r squared in this equation of a circle. Okay, our next conic section is written in its standard graphing form. And notice that we have a plus sign in the middle, and we have both x squared and y squared. Their coefficients would be 1/16 and 1/4. So we know it's not a circle because they have different coefficients in front of the x and the y. So that stretches out one of the axes. So this will be an ellipse. And what do we know about the ellipse by our transformations? The center, we move in the value that would make this equal to 0. So x would be -7 and y would be +1. And think what we know here about the size of our denominators. So if we were going to sketch a rough graph of this, so we just found out our center is at -7, +1. And the bigger denominator here, the square root under the x would be 4. So in the x direction, so we're at -7 here, we would go 4 units in either direction to get to our major vertices. And we would go 2 units up and down to get to our minor vertices. So this is a very quick, rough picture of our ellipse. So the distance from the center to the major vertices was a. So the square root of this bigger denominator. So we've got 4 units on this major axis, the longer distance across the ellipse. And the distance to the minor vertices from the center was the square root of the smaller number. So the square root of 4 became 2. So the distance from the center to the foci, well, that takes a little bit of remembering. Our foci, remember, are these points on the major axis, and we used A and B for these distances to the vertices, so we use the letter C for the distance to the focus. And can you see that in this case C has to be smaller than distance A? So the way we remembered this is it's almost like Pythagorean theorem. For a hyperbola, it's going to be a squared plus b squared. But for an ellipse, C has to turn out to be smaller than A. So we remember a squared minus b squared. So C squared would be 16 minus 4, or 12. So we would take the square root of 12. So from either direction here, we're going to go 2 radical 3 units from the center. So 2 radical 3 units in either direction. Okay, our next problem, I might scroll a bit here, has a minus sign in the middle. So what changes? Our coefficients are 1/16 and 1/4 again. But we've got 1x squared is positive and the y squared will be negative. So this is a hyperbola. Our center, we still have to compensate here for these shifts. So we shift in the opposite direction. And now we've got to think about what we do with graphs of hyperbolas. So now it's not the size of the denominator that matters, it's which one is positive. Here the larger denominator happens to be with the positive. So we use the positive value for our transverse axis. So again, I'm not being real careful with my graphs here, but we've got a center point at 2, -5, and the x is positive, so we're going to travel in the x direction. The square root of 16 is 4, so here we're at 2, -5, so we're going to go 4 units over and 4 units here. And we know our hyperbola is going to be these curves in this direction. Remember, how we know how to draw the asymptotes is to use the square root of the other denominator. So we go 2 units up the square root. So we call this the fundamental rectangle. So we traveled the square root of 16 units horizontally. So we traveled 4 units this way. And we traveled the square root of 4, 2 units this way. So I'm going to erase those because they'll be in our way later. So now that we've got our fundamental rectangle, remember the purpose that served was to give us the asymptotes. So I didn't really ask you to graph this, so I'm doing more here than we had to, but that gives us the shape of our hyperbola now between these asymptotes. So let's fill in our questions. The distance from the center to the vertices, that's this distance along the x, so that was 4, and it is not because it's bigger, it's because it's under the positive term. So if the y squared were positive, then we would have traveled up and down that many units. And the distance from the center to the foci, we haven't done our foci yet. Remember, our foci are on this, is called the transverse axis. And again, we use the letter C. And notice here that A, notice this time, oops, I got my foci in the wrong place altogether. I'm doing another ellipse problem. Our foci have to be inside the curve, sorry. So here our distance C is bigger than A. That's how I caught my mistake. Our distance C in this problem is bigger than A, so let's write it right next to where we did our ellipse formula for foci. Here let's do the equation C squared is equal to A squared plus B squared for a hyperbola to find its foci. So here we've got C squared is equal to 16 plus 4, so the square root of 20, I'm going to write as 2 square root of 5. So from the center to the vertices, center to the foci, we're going to travel 2 square root of 5 units. Is the transverse axis vertical or horizontal? That depends on which one is positive again. So because x is positive, the x coordinates move us horizontally from the center to the vertices. If the y coordinate were positive, we would go up and down. So again, this point is called a vertex. This point is called a focus. This point is called the center. Okay, and letter D. Looks like I lost some space here, but what I notice is that x is squared, but y is not. X is quadratic, y is linear. So this is a parabola, and it is written in standard form, so we know that our vertex is going to be at h comma k. So our horizontal shift is in the opposite direction, so that would be a 1, and our vertical shift is in the same direction, so that would be a 3. Okay, the distance from the center to the focus. Now we've got to remember something completely different for parabolas. The key here is to recognize in this form that we've got this value of 4p, and p is going to give us the distance from the vertex to the focus of the parabola. So let me just make a quick sketch here of what we've got. We know x is squared here, so this is an up-down parabola. Because this number is negative, we know the parabola opens down. So our vertex is at 1, 3, and our parabola is opening down. We don't, in some shape here, probably narrower than that. So the focus is going to be inside the parabola, and this distance is going to be p units, And then we use the opposite of p units to get to this line that was called the directrix. So when we studied parabolas as conic sections, we talked about the focus and the directrix. When we studied them as functions, we didn't really discuss focus and directrix. Okay, so let's see what we've got here. So we can see that if negative 8 is 4p, then p is a value of negative 2. So from the vertex, which was at 1, 3, I want to travel down 2 units on the axis of symmetry. So if our vertex was at 1, 3, this focus would now be at 1, 1. Here the question says, what's the distance from the vertex to the focus? So that would be 2 if you make it positive. If you wanted to show that you're going down and you left it as negative 2, that's okay. But since distances, we would normally do absolute value. All right, the equation of the axis of symmetry, that's this vertical line that passes through the vertex. And the directrix is this horizontal line. The directrix is always perpendicular to the axis of symmetry. So this directrix was 2 units up from the vertex. So this equation would be at y equals 5. So that was a lot of material to squeeze in a small space here. Okay, let's finish this section. Here we just have to identify from general form. Remember, these are not in that standard graphing form now. These are in general form. I notice that x is squared and y is squared. I notice there is a plus sign between them, so that means it's either an ellipse or a circle. And it's a circle if we're going the same direction or the same distance in both. And here we've got different coefficients, so it's stretched wider in one direction than the other. So it makes it an ellipse. Here we've got x squared and y squared, but there's a negative sign between them. So one is positive, one is negative. Even if these numbers, even if these coefficients were both the same, this negative sign makes it a hyperbola. In G, x is quadratic, but y is linear. In other words, x is second power, y is first power. So we know this is a parabola. And in fact, we know when x is squared, it's open up or down. Here, a is positive, so this is going to be a parabola that opens up. Here we've got x squared and y squared, plus sign in the middle, and their coefficients are equal, so that makes it symmetrical, and this graph will be a circle. Okay, I think we're going to stop this video here, and then our next problems to do some graphs we'll do in the next video.